3082 iron ore sampling standard. Setting up an ISO-compliant sampling scheme design on a base study case, and then asking ourselves the question, what is the contractual position? Our iron ore specifications for commercial trade, and finally, a case study of grade and variability compared to these commercial trade specs. Then continuing to set up a multi-analyte where we're analyzing for more than one element in the ISO 3082 sampling scheme design. And finally, some conclusions. Brent, can you confirm if you can see my presentation?
Yes, Willem, it just needs to be shared. You're not on full presentation mode. Maybe just share it again, Willem. There we go, 100%.
Excellent. Okay, Brent, camera back on.
Yeah, we can't see you, Willem. We see your presentation, so you can just put your camera back on. There we go. Just unmute, Willem. Just unmute.
Good. The ISO 3082 sampling standard is a global iron ore sampling reference instrument to advise on sampling scheme designs. In other words, it provides a level playing field for trade in terms of quality variation of the ore, the number of increments required, our final sample mass, and also the typical precision levels we can expect for global iron ore variability for our specific ore. We provide some automated mechanical sampler design heuristics and even some manual sampling applications. But as you would know, in a bulk ore commodity application like iron ore with exceptionally large flow rates, it is not always safe or practical to sample these streams manually. Another purpose of the ISO standard is to try and standardize global iron ores' variability and to provide guidelines how to sample them to achieve a certain precision level. In other words, not measuring only the average grade, but also the bell curve distribution around that. But there could be exceptions where even bell curve distributions are replaced with Poisson distributions. So naturally, not all variation of all global iron ores can be covered in an encompassing umbrella type of standard. The ISO 3082 is one of the best developed and most comprehensive ISO sampling standards. But none of the ISO standard, including this one, goes on to specify commercial trade conditions, like the penalties associated with precision level of measurement, or bonuses on those same parameters, and finally the precision level required for the analytical result. When we set up a sampling ISO 3082 compliant system, we can first see that the ISO standard lists that it has a probability of 95% of finding the precision levels if you follow the recommendations by the ISO standard. That is because not all ores can be generalized into a standard, and that some ores will be more variable than others. If we consider a regime here with shipload sizes of 14,000 tons, in other words, less than 15,000 tons, the ISO standard would typically give us a precision level of 0.55% indicated in the red circle. So if we are an iron ore exporter that requires an ISO 3082 compliant system, and the request is to measure grade with a composite chemical sample. We have a lot size of 14,000 tons, which is a good commercial position to be in. It is a fairly small lot size. An alternative would be to consider maybe 1 day worth of production, which at iron ore production rates would result in large lot sizes. But certainly on this request, which is our design case, we can defend our contractual position by the shipload if we base our lot size on shipload sizes. After some discussions with the client, we now know that the product target grades of 65% elemental Fe will be tightly controlled around that average number of 65, and that's guaranteed by multi-stage processing through run-of-mine sorters, dry cobbing, jigs, wet magnetic separation, reverse flotation, etc. So in our fictional design lot case here, we have a lot of equipment that gives us a lot of resilience to achieve our final grade. And furthermore, this plant will have a cutting-edge process control and online analyzer, also using a Multotec Rama system that feeds representative samples metal accounting standard to the analyzer itself. So our process is tightly controlled, and therefore the quality variation denoted by sigma W would be less than 1.5. Our discussion on precision, the ISO generalized precision levels were preferred by the client, and with a tongue-in-cheek, they also told us that the system has to be ISO compliant. So what question are you asking us around precision level? So the overall precision, first of all, important to understand, is a measure of the combined precision of sampling, sample preparation, and measurement or analysis. It is twice the standard deviation of all these processes. We know from our design case study that we are dealing with small quality variation from our process. In other words, the sigma W is less than 1.5 for this beneficiated or washed iron ore. We then consider table 3 of the ISO standard, which tells us the example of the minimum number of increments required for a desired sampling precision level. If we consider that we have small quality variation ore and we have a lot size of 0 to 15,000 tons, we can conclude in the red circle that we need a number of 25 primary sample increments that must feed into our composite sample to be ISO compliant. There is, however, a parallel requirement, and that is the mass of sample required, not only the number of increments, per particle size fraction in order to give us a certain level of standard deviation compliance. As we can see from the table, as we move from a 40 millimeter particle size down to a 250 micron, the amount of sample we required ranges from 325 kilograms all the way down to half a kilogram or 500 grams for a required precision level of 0.1%. If we require a more stringent, a tighter Bell distribution curve around our average result of 0.5%, we can see from the table that we need much more sample at coarser size fractions to achieve those refined precision levels. So the particle size distribution is not the emphasis of this presentation here today, but it is a parallel requirement in order to comply with the ISO standard. So our final answer then from our scheme design is we need 25 sample increments, and we need those samples taken by accurate, automated metal accounting samplers that are bias-free. To measure the 65% Fe grade with our composite sample at a 95% probability level and to achieve a precision level of 0.55 for a lot size of 14 kilotons, while assuming that our final composite mass is a function of particle size distribution, and in this case designed to be parallel compliant, we may have an ISO compliant sampling regime on iron ore elemental grade. Now at $143.5 per ton, which was the spot rate from a day or two ago, the shipload value would be around $2 million. So we have $2 million on the line for an ISO compliant sampling system. And the question is, are we happy with our design scheme? But what happens when our buyer measures a different grade of iron ore and they can prove to us that their precision level or their standard deviation around their average result on their bell curve distribution is tighter than ours? So overall, they've got a better controlled and more compliant precision and sampling analytical system. Our ship is now docked at the quay of the buyer. Do we accept a penalty? And here I'm guessing $5 per ton, totaling 70,000 tons. Or do we contest that penalty? And if we do, for how long? Considering that we are paying the shipping line demurraging costs or standing costs for being docked at the quay of the customer and not making money for the ship of the owner. Or do we wish to arbitrate and pay international lawyers international fees? And at which international court will these proceedings take place? Or fourthly, do we take our shipment back, considering that normally offloading facilities, onloading facilities at points of export do not have offloading facilities, and we probably cannot offload the ore once it arrives back. Also, we would have paid 3 times for transport to the original intended customer, back to ourselves, and on to the next potential buyer. And then there's more. Here we consider from the S&P Global Platts specification guide on iron ore, a couple of typical grades for iron ore. If we have an IO spot blast furnace pellet premium at 65%, we would need an iron grade of 65. However, if we have a furnace premium pellet, it only requires 64%. But then again, a non-premium furnace pellet also requires 64%. That is because there are more elements at play in the specification than iron. There are also specifications for silica, alumina, and sulfur. And cold crushing is a physical property, which again is beyond the scope of our timeline here today for discussion. We'll only focus on the chemical grades, but certain physical properties are also sometimes required for commercial trade. Given that we followed our first advice of taking 25 primary sample increments per shipload into a composite sample and analyzing that, assume for a moment that we have built that sampling plant and that it is performing accurately. It then puts us in a position to measure from 10 consecutive shiploads, taking 25 increments per shipload and analyzing the composite sample. We can then measure the variability of our ore over the 10 shiploads. On this graph, we can see the iron ore grade measured on the primary axis on the left-hand side, and aluminium and silica grades measured on the secondary axis on the right-hand side of this graph. We can see a fair bit amount of variability in the iron ore, but bear in mind, around an average result of 65%, we only dip as low as 63.5 up to 66.5. However, the relative variability, in other words, the variability around the average value of the aluminum content, is quite high compared to the rest. We also can conclude some variabilities for phosphorus and sulfur content. If our intended sale of product is to sell a IO spot blast premium product, we would need a grade of 65% iron ore on the first row of this table. If we have a look at the analytical results of our ore from our reliable sampling process and laboratory, we would note an average grade of 65.4. And that's good news because we are exceeding the minimum requirement of 65%. However, at a standard deviation of 0.9, some shiploads might be under and some shiploads might be over. The question is what type of penalties or bonuses will we receive in those two respective instances. A silica measure of 5%, again, we are borderline on an average of 5%, but our standard deviation puts us into a 4.5 to 5.4. And what penalties will we pay on that? We can, however, see that our aluminium and sulfur content is on average regularly higher than the required spec. And even though we qualify to sell a premium product on iron ore content, we do not qualify to sell that product on aluminium and sulfur and will probably pay heavy penalties. It might therefore be practical to consider a spot blast premium product at 64% iron content. And here we can see on the right, indicated by the green robot sign, that it's all systems go in terms of our compliance for iron, silica, aluminium, and sulfur content. So in our specific ore case study, we then have to target a lower grade product, which means we'll get a lower premium for it and definitely don't want to be in a position to pay penalties. And now we're going to loop back on our previous ISO 3082 compliant sampling scheme design, which in the beginning was based only around iron ore, but now goes on to include also silica and aluminum content. We saw the standard deviations for our iron and silica ore for the 10 consecutive shipments was 0.9 and 2.8 respectively. If we refer to table 2 of ISO 3082, we note that our standard deviation quality variation there is less than 1.5 and therefore qualifies as small quality variation. Taking 25 sample increments per shipload lot size of 14,000 ton would indeed be sufficient for ISO compliance based on these two elements. However, when we consider aluminium with a standard deviation of 0.48, we can see that the aluminium content falls into what we call a medium band of quality variation. Table 2 then leads on to table 3, and here's where we find the fly in the ointment. When we consider our aluminum content for a lot size in the first two columns of between 0 to 15 tons an hour, and for medium scale variability, we would need 50 increments to measure aluminum content with suitable precision levels, not 25. These are also from table 1, the typical precision levels that we can expect from this newly designed sampling scheme. In our conclusions then, samples must be taken by accurate automated mechanical samplers that are bias-free. Only then will we be in a position to measure the variability of our ore instead of the variability of our sampling, sample prep and analytical process. The reported precision levels from the previous slide are only at 95%, and the ISO standard cannot account for all variabilities. It is best to know the variability not only of your iron ore, but also the other elements in your iron ore before designing your sampling scheme. As a reputable supplier, we may not want to adhere to the absolute minimum compliance of the ISO spec. We may slightly want to exceed that if we want to distinguish ourselves as someone that takes quality assurance seriously and supplies good quality products. Our final sample composite mass is a function of the particle size distribution, which was not discussed in detail in this presentation. And then we need to consider our contractual position, not only on the main two analytes in iron ore trade, namely iron and silica, but also some of the other elements that could include aluminium, sulfur, or phosphorus. Our sampling system and laboratory would have been under-designed by 100%, given that we have to increase our number of primary sample increments from 25 to 50 if we also want to sample aluminum at medium quality variation. But our contractual offtake agreements can be far more complex than the scope of this presentation that covered chemical grade only. The future of sampling, not only in iron ore, but globally, is not to sample in applicability to iron ore, iron and silica grade, but also to sample trace elements like arsenic and lead content that could have environmental or severe health effects. We, in other words, in future will be expected to sample our product, not only for the main elements, but also for trace elements probably present in the part per billion range. Because of these low concentrations, we may at times have some of these contaminants and at times zero. And that rapid variability between 0 and 5 around an average value of 0.1 will give us a large variability index, which on table 3 would then require us to sample 100 primary sample increments. Also, in our contractual offtake agreements, there are physical parameters like moisture, size, and other physical properties, abrasion and hardness that may also be required. It is therefore very important for you as a client and a supplier or buyer of iron ore to determine your strategic level of ISO compliance, to put you in a position to defend against contractual claims. ISO 3082 compliance on one or even all of the elements provided does not necessarily mean that you are exempted from commercial penalties. Therefore, you must base your sampling regime requirements around your commercial offtake agreements. Specify your average values for each analyte, iron, silica, and the rest, and also the tolerable bias levels or the tolerable precision levels around those averages, and be very clear on penalties or bonuses when writing your offtake agreements. If your sampling scheme and your offtake agreement are both written around the level playing field of ISO 3082, that's wonderful. But if your sampling scheme is designed to ISO 3082 compliance and your commercial offtake agreement are written around a different set of rules, you are at major business risk. Protect your bottom line money. Thank you very much.